Alright, 2.7 is on time series data. Time series data originates as measurements usually taken from some process over equally spaced intervals of time happens. So think about time series data. Probes and things like that can be used to measure air pressures over amounts of time, or maybe heat increase or decrease over amounts of time, maybe even blood pressure over different amounts of time. So time series data, of course, relies on time. Now, within time series data, we do have a couple of different terms that you want to know. In a stationary process, the time series varies around some central value. And has approximately the same variation over the series. So that would be a stationary process. Non-stationary process, the time series possesses a trend. The tendency for the series to either increase or decrease over time. That's what the trend would be. It would be the tendency for the series to either increase or decrease over time. Alright, so these are the two processes that time series data would come from. So maybe let's say that data was taken on the amount of carbon monoxide in the atmosphere over the past 100 years. Well, more than likely over the past 100 years, the amount of carbon monoxide would have increased. So I would think that data probably would consistently increase over those years. So then that would be a non-stationary process. Let's say that my A1C was taken every 4 months for the past 8 years, and it stayed around the same value. It didn't. Maybe it was 5.1 one time, and it was 5.8 another time, and then it was 5.2 the next time, and then it was 5.7 the next time, then it was 5.2 again. So it's staying around a certain interval. It's not really increasing or decreasing. Then that would be more of a stationary process. right, so one of the examples in the book, it says batting average represents the percentage of the time a player gets on base resulting from a hit, right? That's how calculation of batting average is done. In Major League Baseball, the better players have batting averages between, we usually just say, you know, what's he batting? Well, he's batting 350, or he's batting 200. Well, what does that actually mean? That comes from, you know, the amount of hits that he has, or percentage of the hits that he has. And a lot of times with batting averages, you'll see things like, you know, like that. They would be referred to as 300 in, I guess, baseball speak. But it's actually a decimal, right? It's 0.300 or 30%. And the better major league players usually have batting averages between these two values. So that means that 30% of the time, between 30% and 40% of the time, whenever they go to bat, they get a hit. Okay? So there is a set of data in your book, and I'm going to show it to you. This is off of the PowerPoint. Of batting averages in different years. It says the time series seems to be wobbling around a central value, and the dispersion around the central value is reasonably constant throughout the series. Thus, the series appears to be stationary, meaning that it's varying between, you know, really between that 0.300 and 0.400, and a lot of times, you know, closer to 0.300. Usually you don't see the really high batting averages. I mean, here's maybe a couple of things that are a little closer to the 400. That was really high batting average for a year. And then you have some that are closer to 300, like here, the 0.312. So you can see these different batting averages, but we don't have batting averages like a 0.600 at some time. They all stay between what we would say in layman's terms or baseball speak, between 300 and 400. You bat between 300 and 400 in your career, and more than likely you're going to make the Hall of Fame. You know, baseball is one of the only sports where you can fail 7 out of 10 times and still be one of the best in the game. You know, you do that as a kicker, you're probably not going to have a job very long. You can, but you know, you do that as a, I don't know, as in any other sport. You make 3 out of 10 baskets on average, probably not going to be playing on your team very long. You're not going to be shooting very much. Okay, so numbers that tend to stay around the same value in a set of data over a time, those would be a stationary process of a time series. Okay. Okay. The next example that your book goes through is on a wildland fire. And in this set of wildland fire data, the data seems to be moving around another central value with relatively constant variation. So this would be, that I'm about to show you, would be another example of a stationary process. Okay, so here's the year. Here's the wildland fires and acres burned between 61 and 2002. While you do have some outliers here, they do tend to be moving around some central value, maybe around 4 million or so, it seems. And it, graph like this, you can probably see it a little bit better, that it is staying, around some central value. All right, an example of a non-stationary process is given in your book as well. Divorce data. Dun, dun, dun. It says that divorce data from the tables that are given shows that there is strong evidence of an upward trend. So I wonder why that is. People just getting married to get married, right? You can see here, back in the old days, we didn't have very many divorces here per 1,000 people. But you can see now that those numbers are rising tremendously. And so it's not like they're varying around one number, going up and down. It looks like they're increasing. So there does look like there's some downward trend starting here. But this time series data would then be non-stationary, because it's not just varying back and forth around some value. All right, are there any questions on stationary and non-stationary processes? Now, the last thing that we're going to cover today is on cross-sectional data. This is 2.8. And think about what a cross-section is. I know you've probably heard the word, but you may not actually know what it means. When you take a cross-section of something, it's kind of like just cutting something. It doesn't have to be in the middle, but if I wanted to take a cross-section, say, of a cell, I would, or that would probably be really hard, but of something, then I would simply, just cut it and then cut it again, and I'd have like this little cross section that I could look at. If you take cross sections of a cone, you get things like parabolas, hyperbolas, ellipses, circles. Get all kind of fun things. Cross-sectional data are measurements that are created approximately at the same period of time. All right, so this is data, measurements, are created at approximately the same period of time. Your book goes through an example. It says, consider the life expectancy at birth in 2000, in the year 2000, for selected countries. And the data is given in a table. So, like, if we're looking at life expectancy in the year 2000 for some given countries, think about it. You could get different ages, life expectancies in different countries at that one time. So that would be like a cross-sectional study, or the data that you collect would be cross-sectional data. So this says that if you lived in Afghanistan in the year 2000, your life expectancy, that means what they expect you to live to, it says is 43. Whereas if you lived in Australia at that same time, the life expectancy was 79. It says the life expectancy in Botswana is 36, or was 36. Could you imagine that? But somewhere like the United States or the United Kingdom, those two countries, it says they're both were 78. So data that's taken at the same time from different places, that would be like a set of cross-sectional data. And so that is actually the end of chapter 2.